Okay, so what I want to do now is to go back to my first lecture, and so we're going to go back to the approach to Operads via evaluation operators. Talk a bit more about this characterization of Operads, and then use that as motivation to spell out Lurie's definition of continuum. So, at the end of the last lecture, I have the following position that E from E to the star is equivalent to the star to the category of operators for some operator O. The following three conditions hold. So, firstly, you want that E has E coefficient less than that. Secondly, given some object X in the fiber N, and the coefficient left of the H square I, we have projections from N to 1, and then another object Y, and the fiber N. We have a fallback, right? The point for United X is the fallback of the product of the home from the right hand side over the mass in 596. The fallback in the third condition said that given some list of objects, each one for example in the power of 1, there exists an object X in the fiber of N with repetition morph between X to Xi over okay, so now some consequences of these conditions. So first of all, we have these coefficient lifts of inerts. In particular, I can use those by to these master Y. So the coefficient lifts of the master Y give functors in the fiber N to the product N copies of the fiber of 1. And so condition 3 says that this is eventually subjective. But then you can also use condition 2 to show that this functor has to be fully faithful. So this is actually equivalence. So this is an equivalence balance. And I also want to note, like maybe this fallback square is a little mysterious the first time you see it, so that's another way to think about it, given these coefficient lifts of the inerts. So let's say I have so given the sum map phi N to M, this would be a fallback if it's a fallback, if it's in a isomorphism on the fibers over a phi. But if I don't think about what this is happening in the bottom row, I can look at I'm looking at the compositions rho I phi from N to 1. And I can use my factorization system to factor that map as something you know. So I enter in I, and then I have an active map, which is then the unique active map from this side to 1. And so conditional 2, I'm back to state that if I look at the set of morphisms from y, x over 5, then after 5 in front of point sets, this is the same as the product from n of e. Well, we firstly say that it's the same fund from y to xi over this composite on phi, but then I can use the fact that I can pick the Cartesian morphisms over with pi i's. So I have Cartesian maps right one over pi I. And so I get my morphism in this direction. With the product of the points y and etc. But now these are humps over the alpha and I. So, in other words, what condition 2 means is that morphisms over phi are given by a list of morphisms over the active map to 1, which are the ones that we want to think of as the multimorphisms in the corresponding operads. So, condition 2 tells us, well, given these Cartesian morphisms from point 1, point 2 is saying that a morphism in E is the list of multimorphisms that we want it to be in our definition of the category of operators. So we just say a little bit more of the proof of the proposition. So, we have I had not right. Oh, I want to check that we've operated satisfies these conditions. So, well, we want these Cartesian morphisms. So, at point 1, we want to check that. Let's say I have some map 5 from enter and this and that. And I have some x in the fiber of the plane. So, and this is the plane of x in my Operad. Then I claim that you can make a map with the prime, but that's the list consisting of the 3, 1, 3, with the corresponding multimorphisms. Just eventually maps. This is going to be Cartesian. And this, we'll just leave that as an exercise if we do that. And then when I rephrase condition 2 in the way I did here, we see that it really does tell us that it really says that the maps in our category operators have the description that they should have. This list of multimorphisms or the things over active maps. And then point 3 is some results. So for the converse, given this functional p from the pointed sets, we want to define a product O. Of course, we take the objects or colors of all moving objects in the fiber of fluid 1. And then morphism should then be an active map. The target should then correspond to an morphism in E that lives us in the active. So morphism. One, 7, Y is maybe by choosing steering S on X in EM with the precision. Well, I choose X in EM such that with the precision left for Y to my list here, and then I have an active map. So I have a mapping morphism O over the unique active map of N from N to O. So if you look at this too carefully, you start to then realize that this is the choice of this X is not unique, it's only unique up for unique isomorphism. So really this is going to give you like groupoids of operations that are weakly equivalent to sets, and then probably just take isomorphism class of these things, which is fine. But maybe at this point you're starting to get everything is obvious and you really don't want to write out all the full details of this. Okay. Then I compose these things. So doing something like this, it's one, and so given a bunch of these things that we're supposed to compose, so this Y is supposed to be projecting to Y1 through Yn. And check that there exists. Sorry, this. Show that there exists some X with I have to look at there's a M, the sum of that and then so then there are inert maps. This has inert projections to the M I. And then I have to find some X with inert maps. The diffusion of this and then finally I can compose. Well, then I use my condition 2 to build X and Y that decomposes to these X. Then finally I compose this X and Y with no first one. Okay. I don't know, does that make any sense at all? But basically, you sort of go back, in defining the category of operators, we started with the operatic composition of multimorphisms and turned that into a composition in a category by making our morphisms be lists of multimorphisms. And now we're kind of just going backwards. We take our multimorphisms to be maps over the active maps to 1. And then we use the decomposition coming from the inert coefficients to turn the composition in E into a composition of multimorphisms in an operad. Okay, so output of all this is like, as I said, this way, so if you can identify the category of operads and functors, create a subcategory of that objects, these objects are those that satisfy the 3 conditions, and the morphisms are those entities over finite sets that preserve the inert coefficient morphisms. Okay, and I also want to point out we can characterize in a nice way this model those operads that come from symmetric monoidal categories. Given P from E from the set, the following are equivalent. 1 is equivalent set to op of the op. So E is equivalent, so the first condition is that E is equivalent to the category of operators of the operad coming from a symmetric monoidal category. 2, E satisfies our 3 conditions. And also, it's a Focacci condition. And finally, we already know that P is a Focacci progression. We can simplify conditions 1 to 3 quite a bit. P is a Focacci progression. And you just have to have this identification of the fibers. So E of N should be equivalent to product of any copies with 1 via the Cartesian lifts of the projection for 1. And moreover, we can identify maps. So we saw yesterday that maps between operads of this form, the opt, corresponding to lat symmetric monoidal functors. So those will correspond to maps between these kinds of vibrations that preserve inert for Cartesian morphisms. But we can also identify the strong symmetric monoidal functors. Those correspond to functors so that preserve all of the Cartesian morphisms. Maybe I would say I won't go into the proof of this, but just to give the idea of where we get the tensor product from, the point is that if we have now our we look at category of operators with O. What does it mean that this is actually the Cartesian part version of a final pointed set? That means we also have Cartesian morphisms over actives. So in particular, we have them over at least alpha n. So if I have if I look at a multimorphism, then through Y, this is a multimorphism O or a morphism over alpha n. This has to factor as a Cartesian morphism, so there exists a canonical morphism to some object I call the tensor product of its lines, such that multimorphisms are the same thing as morphisms in like unit operations from that thing to Y. Like, so multimorphisms are represented by some object that we think of as being like this. And then the fact that Cartesian morphisms composed tell you that this really is sort of an iterator. You can decompose this as like this representing object really is a tensor product, where the tensor product is the thing that. And if I think about like x, there's Cartesian morphism from like x comma y, x tensor y. So all binary operations, the same thing as just ordinary maps out of that. But then, because Cartesian morphisms compose this object here, I can think of as obtained by iterating batch construction. So it's so that's where the symmetric monoidal structure comes from. Okay, so if you buy all of this, that I don't think I explained very clearly today, but it is true, then you can regard this here as a new definition of Operads. That I think you can argue has some advantages over the classical definition, even in one categorical setting. So in particular, it's like it's a very concise definition. I can write it down quite quickly. And it's like really precise. I don't have to say anything about some obvious diagrams of sigma m actions commuting in a way that no one ever wants to worry about. And I would also claim that this is, once you get used to it, it's a fairly easy definition to use in practice for many purposes. Not saying all, but like in particular, if you have to define some symmetric monoidal categories, it's quite reasonable to write down some category with a function to define unpointed sets and check that it is a vibration with these properties. While in some sense we're specifying more data than in the classical definition of symmetric monoidal category, in this way it's packaged in a way that's actually reasonable to write down. While it's not very common that anyone writes down the full set of data that you're supposed to write down to define a symmetric monoidal category in the standard definition. But anyway, the main point here is that we are working entirely within the framework of normal categories and like things we can define there. So this makes this definition very easy to generalize to infinite categories.
Can you say one more time what you mean by this tensor product x1 v tensor xn? What is it that you want to say?
Right. So let's say I have like maybe it's easier to say I have some Operad, and like I want to figure out when does this come from a symmetric monoidal category? So you want to say that there exists some objects. So first of all, you want to say that like multimorphisms from x1 to xn to something are representable. So there exists a canonical multimorphism x1 to some object that we might call a tensor of x1 to xn. And so I will say that only represents multimorphisms. So multimorphisms from this list x1 to xn to some y are the same thing as morphisms in the underlying category of the operad from this tensor product object. So this you might call as the representable operad, and then there's the second condition, which is saying that if I want this object to actually be obtained as an iterated tensor product like binary things. So one way to say that is that if I have a bunch of lists of objects x1 to xn, then you consider the tensor of x1 through tensor of xn. So I get a morphism like this. So I can compose these canonical maps for my lists big x1 through bxn, and then I get the canonical morphism from the list of those guys like this. But then now I have a morphism from this big list to a single object, and so that's supposed to factor through tensor of sort of the union of the lists. And so I get a map from that to that, and that has to be an isomorphism. So that's the characterization in terms of like the first definition of operad I gave of when it comes from a symmetric model category. And then if you translate this into the category of operators, you're supposed to get this condition that it's a co-Cartesian fibration. So does that help? Like this special morphism you're supposed to get from taking the co-Cartesian morphism out of one to xn equal n, n, and then I have a co-Cartesian morphism out of that over alpha n, which is this tensor. And then like this condition of representing the multimorphisms, well, basically says that that's a locally co-Cartesian morphism, and then this one is saying that the locally co-Cartesian morphism is composed, and therefore they are actually Cartesian. Okay, so let me write down Lurie's definition of the Operads. In the Operad, it's function of the categories. Text. Such that we have the analogs of the condition to vote. So one E has interpretation lifts. That morphisms. Two. Yeah, I don't want to write down this square again. I guess it's even still on the board over there. But there is nothing close to this. Operads. And again, by the same argument as I sketched over here, you can say that's saying that the fiber of the mapping space or something in finite pointed sets decomposes as a list of multimorphisms. And then finally, I guess I wanted to call my function over. This is supposed to be an actual upload now. Right. Again, you're going to objects and so on, so that's it didn't go wrong. There exists and gets in the end. It is type of diffusion over and then a morphism infinity operads. It's a fusion of triangle. Where F must be about the diffusion of some nuts. And we will also refer to this as an O algebra in P. Especially in the case where P is a symmetric monoidal infinity category, which I will provide. Now we can define the infinity category of infinity operads. This is a subcategory of infinity of infinity sets. You can also define, given two infinity operads O and P, you can define an infinity category with O algebras and P as a full subcategory of functors over finite function sets in O to P. That means a morphism of O algebras and P is going to be a natural transformation. It's living over function sets like this. Right. It's a bit more likely to make this into the mapping infinity category, so then infinity 2 category of infinity operads. Right, so give sort of a trivial example, namely O is an operator in sets. Then if I take its category of operators, this is an example of infinity operad. So for example, we get take O to be the commutative operad, and that just gives you final pointed sets to the identity. The social operad, or the other examples I guess today, so the commutative algebra for the module, or the bimodule operad, or whatever. And so now, like the good thing about this theory is that if you just take algebras in a certain infinity category for these set operads, the fact that we're working in the fully homotopy-coherent setting of infinity categories means that we just automatically get the fully weakly coherent notion of these structures of commutative and associative algebras and so on.
It's an example of a number that will not come from symmetry.
These still come, well, except for com, these still come from something another variant. Or the EM operator, for example. And there are also ways of thinking of operads as certain symmetrical categories, just an extra structure, but that's another story. I'm not sure, did I answer the question? Or... Sorry?
Associative.
And actually, even if you say the commutative opera, that one happens to come from a symmetric monoidal category, but the symmetric monoidal category is like the point. Yeah. Okay. If you think of maybe that makes the difference.
Okay, and then I want to introduce symmetric monoidal infinity categories, but you know, it's going to follow by taking that proposition over there as a definition, basically. But we can do it a little bit differently. We do this in terms of definition that reflects to Segal, in a sense, which is if we have some infinity category C, we find a product. Then a commutative monad in C is a pointer of M from S into C, such that I look at the value at N, I can use the nut maps that I keep. For another math is row 1 to the N. Is it a map to the product of N copied by of 1? And my condition is that those maps have to be equivalents. So the value of my functor N should be decomposed as a product of n copies of M1. Then this is an equivalence. And then I can define the symmetric amount of infinity category. We can give it one of the infinity category. I don't know if so the idea is that again, like the active maps are going to tell you the commutative multiplication of this the structure. So you're going to have the active map from 0 to 1. I mean, the value of n at 0 has to be a point. The product of 0 copies of n1. You can get a map from the point to n of 1. That's going to be the unit of our multiplication. And then with a unique map from 2 to 1, which gives me an application map from n of 1 squared to n of 1. And this is commutative because in finite pointed sets, this map is unchanged if I compose with the homomorphism of bracket 2 that swaps the 2 non-base points. And then looking at 3 to 1, you get that this is associative and so on. The heuristic idea of why this is commutative monoid. Right, and then so I can also think of this pointers from finite pointed sets to infinity are the same thing straightening equivalence as permutation vibrations over finite pointed sets. And so I can also think about symmetric model infinity categories as certain permutation vibrations satisfying this same condition. And then you can show the following analog of the proposition up there that if I have a permutation vibration of infinity categories, P should be infinite star. Then the condition that P is an infinity operad. If and only if P is a symmetric monoidal infinity category, that is it. It's the straightening of communication. So symmetric monoidal. So first of all, I'm going to be inflating the when I say symmetric monoidal infinity category. I'm going to sort of conflate functors or vibrations, and well, most of the time I'll probably off. And somehow, to start with, it's nice to define them as commutative monoids in practice, is a bit clear that's the right notion of being symmetric monoidal, but then in practice, you end up thinking about them as vibrations a lot. So I was probably to say symmetric monoidal infinity categories for the corresponding vibrations as well. So symmetric monoidal infinity category with underlying infinity category C. So C would be the value of my functor at 1. What else can we want to C tensor or maybe I should comment on this is the point where I disagree with Lurie about notation, because he also will use O tensor for a general infinity operad, and then he will use O as the fiber of the infinity operad 1, even if it's not symmetric monoidal. But I think that's it's convenient sometimes, but it ends up being kind of a weird convention that you end up having that En is there's an infinity operad called En tensor, and then En is actually just a synonym for the point because that's the underlying category of the En operad. But I will use O over finite pointed sets for general wrong thing with buttons. Right, and then let's be mindful. Expect from what we said already. Black symmetric monoidal functor we can think of as isomorphism of infinity operads. Or triangle where F is not completely morphs. It's strong if it also potentially presents for competition. So we have this formalism of infinity operands, and like a lot of the time, what we're interested in as our algebraic structures might just be sort of these classical ones that we're used to, like commutative and associative algebras and modules and so on. But on the other hand, having this infinity categorical language gives us access to a lot of constructions of sort of symmetric monoidal things that we can look at those algebras in. So, so one thing that I want to sort of like, I'm not very good with examples, but like one thing I will try and mention in the next few lectures is that there are some interesting examples of symmetric monoidal infinity categories that we can obtain by a bunch of general constructions that I'll mention. And so in the last minutes of this lecture, I want to say a few words about one example, which is Cartesian symmetric monoidal infinity. Basically, the idea is that C is an infinity category of finite products. Then there should be we should be able to turn the Cartesian product into a symmetric monoidal structure. So there should be this a in some sense unique symmetric monoidal infinity category. Cross. And with the Cartesian product. Tensor. And then also, if I take some infinity operator O, should be able to describe O algebras in C cross in a simpler way. And certain functors from O into C. Why should we be able to do that? It's like a very vague idea, maybe. If I have O to C cross, let's say I have some multimorphism Y. So an active morph, so something from this thing O1 to the N, which is equivalent to N. And then this is a morphism over the unique active map from N to 1 of N. So this is a multimorphism in O. Well, in C cross, this gets sent to F of x1 equals n, which, because we have the algebra, because this is an algebra, this the fact that F takes inert morphisms in O to inert morphisms in C cross basically tells me that I preserve this list decomposition, so this is the same as fx1 times n. And then I have a map from that in C cross to y, which is the same thing as a map from the product of f of x1 with f of xn to y. Therefore, this is just a morphism in C. So the idea is instead of specifying it. So basically what we end up giving for this operation is a map for the product of f of x to I to fy, with so there's like an neutrality where I can describe this by saying we have f of x1 to f of xn, and I want that object to directly be an object of C, which is a product of f of xi, and maps to f of y. And this is captured by the definition of an O monoid. So the O monoid in C is function n from O to C, such that union of x and O n, with x to xi, with the fusion of OI. Now, the value of n of x decomposes as a product of n of xi, where this map comes from these, inert co-partition maps. So as an example, if I put O to be finite pointed sets of the terminal infinity operad, I get the notion of a commutative monoid that I had on the board over there. We're now going to sketch the construction of this C cross, but I have 5 minutes left in this, so I'm going to spare you from that. Instead to say what the result is. So say symmetric monoidal infinity category. Tensor of star. It's called a Cartesian symmetric monoidal infinity category. First of all, the unit object one in C, it's a terminal object in C. So to obtain the unit, I start with I have C tensor at 0 is a point. And then I have my unique vacuum map from 0 to 1. And I have to have a co-Cartesian lift of that. So there's this object. I think of this as kind of this object being an empty list. And so there exists a co-Cartesian morphism in the empty list to some object in C, which is the final one. And that's where you get the symmetric monoidal unit. And then the condition is that that's a terminal object in C. And finally, since this is terminal, I have to treat objects x and y. Look at x tensor y. And then I have canonical maps from x to 1 and y to 1. So that gives me maps to x tensor 1 and one tensor y. So say I have maps to x into y, and we should exhibit tensor y as the product of x and y. Okay, so then we have the theorem from our algebra that if C is the infinity category of finite products, then there exists a unique Cartesian symmetric monoidal infinity category structure on it. And well, for infinity upon O, all algebras in C cross are equivalent to all monads in C. This in the last 0 minutes, very quickly mention a variant we can make the structure. Which is the complete tensor product. So you can say that the infinity hat is just like large infinity categories. And then instead of that, you consider the subcategory of co-complete infinity categories. And functors should, of course, like preserve small coordinates. Then we have constructed infinity hat as Cartesian products. So there exists a symmetric monoidal infinity category, infinity hat cross. And then I can look at the subobject of that. I'm going to denote as hat infinity co-complete tensor. And so this will have objects corresponding to lists of complete infinity categories. But then the morphisms, well, they're given by, a morphism in cat infinity cross will be given by a list of things that look like functors from C1 cross C2 up to Cn going to D. And so I restricted these CIs and D to be complete. And this stuff functors on this. But now I want to impose the condition that F preserves elements in each variable. I fix all but one of the variables in the source, then I get a column preserved functor. F then. Then the point is that it's now kind of easy to check that this infinity tensor is an infinity operad. So basically, to construct this as a symmetrical, the goal here is to construct a symmetric monoidal structure so that like maps out of C tensor D are the same as like we want this. It's like this symmetric monoidal where it maps the coordinate preserving maps and C tensor D being the same thing as maps in C cross D to E that preserve coordinates in each variable. So basically, to show that we know it's an infinity operad, and so to show that it's symmetric monoidal, we basically just have to show that there is such an object that represents the sort of multi-coordinate preserving functors, which is sort of a separate problem from the constructing the symmetric monoidal structure. So sort of the only representing objects exist. Anyway, I'll stop here. I don't know if that made any sense. Thank you.